Okay, 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 as Pee Wee Herman would say. Uh, Here's my setup for the, I'll call it my Franklin oscillator, and it's going to have a temperature heater, a PTO in it. Right now, I've done two tests. I did the oscillator with the case with this part removed, with it open air, and after with the temperature of this room's a 10 by 10 room. Very important now. This is the test bed. The room is part of the test bed. It's a 10 by 10 room. It's cold outside. It's got electric heater register. Now with this room, with stabilized temperature and the oscillator, open air, stabilized, it drifts about 10 hertz per hour. That's incredible. All right, but to get there, when you first turn the oscillator on, the components in the oscillator have to warm up. Now I'll show you that. Now I've been coming in late at night when I get up to pee. I come in and turn this on. I let this room get real cold, and now the room is warming up. And last night when I shut this off, it was at 2.5 megahertz. Now you'll see when I turn it on. Let's see if it's in the frame. Yeah, it's 133 hertz off, which is nothing. It really is nothing. And that it will stabilize and be within 10 hertz. Excellent. The Franklin's excellent. And I must warn you, I'm working an oscillator that goes between 2 megahertz and 3 because I'm simulating a Collins circuit. Go look at the Collins circuit. It's very important to look at the Collins, is it 51J-1? They take the incoming frequencies and they go into a mixer and they beat down in frequency. So then your local oscillator will be lower in frequency. The lower in frequency that you have an oscillator operating at, the less it drifts. Or should I say, the less the components, when they vary with temperature, affect the circuit. So at a lower frequency, a 10 picofarad shift in a capacitor won't affect the oscillator as much at a lower frequency as a higher frequency. 10 picofarads of shift is a lot when you get up, say, 12 megacycles or megahertz, whichever way you want to say. So I'm going with the Collins idea, with the PTO. Now, Collins PTO is, after it warms up and everything stabilizes, I think it was under 100 hertz. The Franklin oscillator, solid state, is even better. It just is better because it's solid state. It's not warming up. The tubes aren't expanding and contracting. It uses FETs. So that's what I want to tell you. I did a lot of experiments so far. Now I'm going to give you a little bit of eye candy if I get the camera right. I'll show you the inside of this thing. Let's get our light over there. There's always stuff in the way in this room. See, this room's a 10 by 10 room. You know, I don't have that $40,000 lab that other people seem to have. But basically, you have that double ferrite. I stacked 2 ferrites. These are just standoffs, and the DC comes in and goes right to those standoffs. One's minus, one's positive, and on this standoff, these 2 standoffs is where the PTO is going to be, and I gotta take this down out of the way to make room for the PTO. But the PTO will go right in here, and that'll warm this up. And what the next experiment is about is how fast, with the heating the unit up, how fast does it stabilize and then stay within 10 hertz. That's where we're at. But I just want to show you, I finished it, and this is a 6-to-1 tunable capacitor. It's got 2 FETs down there on the perf board. There's a Zener diode. There's a 6.2 volt Zener diode. Even though this is a regulator supply over here, you come in here and it's got its own little regulator. So this thing is overkill for almost all radios that you could build. And that's what I was shooting for. I kept saying, I kept thinking, why haven't I found the Holy Grail? Why haven't I found someone that's done coal pits, Franklin's, Claps. There's Hartley's. There's all kinds of oscillators, and each one of them has an advantage. Now, if you keep digging deeper, you'll find guys that get into phase noise out of an oscillator. Now, I want to tell you something about the real world. If you can't hear the phase noise from the radio from across the room, it's not there. Don't put a scope on it. I had a friend, he died last year, and he owned one record. He built this incredible stereo system, and he only owned one record. He was into getting the most bass, and he went off on a tangent. And he would come over to my house, and I had all these records, and I would sit there for hours at a time, just listen to records with my headphones on, so I wouldn't annoy my parents. And he couldn't get into the music. He got into the technology, the spec sheet. He had a reel-to-reel deck, Sony, and they actually came to his house and did updates on it. That's what he was really into. And I'm into, how does it perform when I'm sitting across the room? I don't want to see a scope on anything. I won't go off on SDRs, but in other words, I have a problem with SDR radios. Anyway, how well does it receive the station? Can you listen to it without getting a headache? There's a lot of shortwave radios that are so narrow. When you put on a shortwave station that has music, it's horrible. It gives you a headache, and that's because that radio was designed for ham or commercial transmissions. It wasn't designed for music. So you gotta say to yourself, what do I want, and what is it going to sound like from across the room? Don't go off into specs. Oh, this one here, it's got so many microvolts. What does that mean from across the room? It means that when something's got slightly better microvolt sensitivity, they'll put a meter on it, and they'll show you, look, this radio is picking this station up 3 dBs stronger. So I always tell people, well, you want to fix the radio that's a little weaker, make the aerial longer. They don't want to hear that. See, when you're selling stuff, you're selling specifications and hype. There's a lot of hype involved. Now, I could not find good information on oscillators, which one's better, because all the really good books are written for tubes. As we got into transistors, no real engineer sat down and built all the different oscillators and said, here, if you want this, this is the one you want. You'll find parts of that throughout the internet. Now, there might be a Holy Grail book that I missed, but in other words, I got into Franklin oscillators, and more people are discovering them. They've been around a long time, but nobody's had the request for one. Now, why am I doing all this? Well, I have in the frame here, I don't know if this is the eBay frequency counter. Now, it puts out noise itself. So the goal was to build a really good shortwave receiver that didn't create noise. So when you tune between stations, the only noise that was on that radio was atmospheric. I have R71As. I have a whole closet full of them. I got heavily into those. They're dirty birds. As you go up and down the band, you hear the noise of the encoder and the oscillator, and you can mute that out, but it's still freaking there. So after they went digital on radios, they started saying, well, let's get some of that noise out. Some of them just mute it. It's still really there. So I started thinking, well, what is the best radio that you could have that doesn't have processor noise from the microprocessor, doesn't have noise from the frequency counter? Well, it turned out to be that stupid Collins I bought. And also the Collins R390. It's a boat. It's a big, heavy radio. But the radio itself has so many pluses going for it, if it's in good condition, that would be your go-to radio. But it's not portable. And the other problem with shortwave and all this that we're doing is there's no real use for it anymore. There's nothing really on the shortwave bands that you'd want to listen to. So it came down to, like, I got heavily into this. It became a rabbit hole. let me make an oscillator. Let's see how much it drifts. I went in the drift rabbit hole. And I started finding other people that are building Franklin oscillators, and they have all these extra parts, and they never mention once that, oh, it's within 10 hertz per hour if the room temperature. No, they never tell you what the drift factor is. They just obsess with these parts, and I added NPOs and, you know, and negative temperature coefficient capacitors. And I'm reading, I'm like, where's your specs? Why did you do all this? What was the goal? What did you achieve? No. And there was one guy, you'll find it on the internet, he built an oscillator into a box, into a steel box. And he said basically, you can build a tunable oscillator that's just as accurate as a crystal oscillator. So you start going trying to find out, well, how much does a crystal oscillator drift? That's another rabbit hole you'll fall into. A crystal oscillator, as it stands, drifts. And you're like, no way, it's crystal, it's fixed. No, it drifts. They're really good crystal oscillators. You can buy them now. They're little tiny four-legged things. They have an oscillator in there, and a crystal, an oscillator, and an oven. And that's so many parts per million. And I have those. I use the 10 megahertz one for calibration. And then you start thinking, well, that's 3 parts per million. Holy crap. You know, that's almost like the WWV standard. And for most people, it's overkill for almost all projects. And where these things came from was GPS. Okay, GPS, they started saying we need the really good references because we got to tell distance. And anyway, that's where a lot of this stuff come from, these little oscillator modules. So I went back and I'm thinking, well, how much does an oscillator drift? And then you realize nobody ever says anything. I'm going to tell you right now, the Franklin at 2.5 megahertz, 10 cycles per hour with the room temperature stable. Once you adjust it in, 10 hertz. And that's overkill for almost everything you're ever going to build. Unless you're doing GPS with it, then you might want to consider some type of module with an oven. Now I'm going to add the PTO to this thing in there across those. That's what those terminals are for, is to hold the PTO approximately center of the unit. And that will heat the unit up faster. And then I'm going to run some more tests. But this video is for people that are really out there. I'm going to tell you right now, when you go out or into the frequency drift rabbit hole, and you notice that you have all these people building stuff, and they never give you any specs. I'm telling you, the Franklin at 2.5 megahertz, you should get it within 10 cycles per hour. It drifts up and down. And it's when I first turned this thing on, open, it was staying within 5. Within 5 for the first half hour. Then it started to move a little bit. But I'm sitting there going, putting those components in that little metal case, did that really make it better? No, it was just a coincidence. Everything on the bench had been the same temperature. The room had reached temperature. And as I'm sitting there, we're within 5, and I'm realizing the room's a little too hot for me. I get up, I turn the room down, or I turn the heat off, and then I start seeing it affect the oscillator. So room temperature is very important. If you're a nut job, if this thing drifted 100 hertz, you would not hear that on a shortwave station that with voice or music. You would slightly hear it, maybe if you're like a real nut job, you could hear the person's tone of voice on sideband shifting a little. And if you're a person that has music notes, oh man, they're perfect, not tone deaf, the opposite of tone deaf. But anyway, there's people that can hear a music tone so perfectly, they would hear a shift of 100 hertz. But the average person's not going to hear it, more than the average person. And that's why, I've been around people that got fixated on stuff. I slightly get fixated on things because I realize when I go looking for the information, I can't find it. And then it starts to bother me, and I start asking the questions. And then the questions in my head, and I did not enjoy building this. I did not enjoy bending the box. See, I showed you guys everything I went through to get to this point. I showed you what the PTO looks like. PTO, PTC, PTO, no, PTC. Here it is here. This self-heats and self-regulates. That's it. It's going to go right in there. And when I turn the switch on for this oscillator, this is going to heat up the inside of the case, and I'll see how much it helps me. Then I'll tell you what happened. Like I said, I've actually found people that have put ovens on crystals, but they never mention what it did. Look at me. I added an oven. I got it regulated. I have a temperature. Well, how much is it drifting? I don't know. What was the point of the whole thing? It was to make an article just to show people your equipment. Now look at my equipment. Look how pathetic this is. You know, because I try to be practical, and this oscillator, I just enjoy the Franklin oscillator. I discovered it, and the reason I like it is it runs on 6.2 volts. You can get a wide range of frequency that you can variable. Now, of course, down in the low frequency, this thing goes, I think it goes up to, let's see how far it goes up to. I know it goes down to 1.9. I never even went all the way up. That's down. It goes below 2. That's what I want. Let's see how high up it goes. Are we in the frame? 3, 4, 5, 6. Okay, so it goes from 1.9 megahertz to 6.6 megahertz. I think that's it. All right, that's it.